Okay, we are now recording. It's my pleasure at this point to introduce you to our speaker, Eric Ma, who will be presenting Magical NumPy with JAX. Let's give him a warm welcome and have a great day. Enjoy the tutorial.
Okie dokes. Hello, everybody. Welcome to the tutorial, Magical NumPy with JAX. I'm Eric, and I'm going to be your instructor. I wanted to say a few words about the format of the tutorial, just so that nobody freaks out when you see what I do here. I've known one thing that's really important is the format, and I've known that as an online speaker, I actually get a bit of a gag reflex whenever I speak for too long. So what I've chosen to do to make sure that the tutorial runs as smoothly as possible, especially with respect to the explanation pieces, is I've decided to make sure that all of the lecture portions are pre-recorded so that I don't like midway start gagging up or something, right? So this is just to make sure that the tutorial lecture portions they run as smoothly as possible. With respect to how we're going to conduct this tutorial today, there's a few things I want to make sure you're set up with. The first is I'm sharing on my screen a link to the official website for this tutorial. It's called DL-workshop. I'm going to drop a link in the chat. We'll see it one more time in the video for the benefit of those who, in the introductory video for the benefit of those who join in a little later. Head over to that URL and you'll find all of the content that's going to be there. In particular, of the tabs that we have on the left-hand side, the ones that we'll be going through are actually the JAX programming idioms. So I'm going to zoom in just a little bit so you can see over here. It's the JAX programming idioms, and those are the notebooks that we will be going through. Okay. I actually do appreciate that we have Thomas, who has his video open. It actually helps me, Thomas Knox, who has his video on, because it helps me with the visual feedback that, like the heading of the nodding of the head and that sort of stuff really does help in an online setting. So I definitely appreciate that. No pressure though. If you prefer not to be recorded, definitely don't feel pressure to turn on your video. Okay, and so with that, we're going to launch into the first lecture. After every lecture section, there's actually time allocated for hands-on exercises and interactive, you and me interacting together. You can ask questions live, you can ask them in the chat, totally whatever format you're comfortable with. If need be, I've got a whiteboard link that I will drop in as we need it, right? I don't want to complicate matters early on, but there will be a whiteboard link. And the final thing before we go on is, in case anything happens to me or my internet, I actually have a link to all of the pre-recorded lectures in a public Dropbox folder. And I'm just going to repaste it in the chat one more time. That's like the backup to the backup to the backup. All right. So in case anything happens, the worst case scenario is Mike can play those videos in my absence and then say, here's 20 minutes for exercises. I hope we don't have to go there, but it's just in case. All right. Just want to make sure we're covering at least even that base. So let me just drop the link to this folder over here. So copy link and then paste it in the chat. And so this is for the oh, sorry. Let's try that one more time. There we go. So that's the Dropbox link. Like I said, it's the backup to the backup to the backup for the absolute worst case scenario that I drop off completely from this tutorial. I'm pretty sure we won't get there, but I just want to make sure that base is covered. Okie dokes. With that, I'm going to start by playing the first lecture video. It's the introductory video. And then I'll open up a little bit of time for any logistical questions after that video. So let me stop the screen share. And then let me see, share my screen with sound. We'll do desktop 1 and I'll do this video over here. All right. So here we go. Hi everyone, welcome to the tutorial, Magical NumPy with JAX. My name is Eric and I will be your instructor today. This tutorial is all about NumPy and JAX and all the ways that the package JAX makes the NumPy API pretty magical. Now, before we go on, I'd like to introduce myself a little bit. I'm a practicing computational scientist, colloquially also known as a data scientist, and I primarily work in the worlds of biology and chemistry. What keeps me going in these fields is actually understanding how biological and chemical systems work through the lens of computational models. Believe it or not, JAX's extension of the NumPy API and its reimplementation has been incredibly helpful in this respect. Apart from that, I also enjoy speaking and teaching on technical topics. At previous PyCon, SciPy, and PyData conferences and meetups, I've spoken on topics such as data science workflow, Bayesian deep learning, statistics, and reliability practices for data scientists, as well as taught tutorials on network analysis, deep learning fundamentals, and Bayesian stats. My main motivation for doing all of this is actually learning in the public. These are topics for which making a talk or tutorial has helped me to learn them properly, which also helps me help others to learn them too. And that, my friends, is why this tutorial on JAX exists. So what exactly is JAX? Now, if you go to the official JAX repository on GitHub, you'll see this exact line, that JAX is a system for composable transforms on NumPy programs. Well, what exactly do we mean by this? So my hope is that by the end of this tutorial, it'll become a little bit clearer. From the perspective of a user of JAX, I see it as something that supercharges the NumPy API. It allows me to do things like 1. Write non-trivial array operations that might otherwise involve loops and magical access numbers. 2. Automatically obtain the derivative of a function that I write in NumPy. And 3. Just-in-time compile that exact same code to make it run really, really fast. The overall effect of using JAX is that it helps me to write code that is much easier to reason about. With colleagues and interns, we've leveraged JAX to actually learn about the internal structure of certain models, such as graph neural networks, recurrent neural nets, hidden Markov models, etc., etc. Moreover, the JAX ecosystem keeps growing. If you look around online, you'll see that DeepMind, which is a Google subsidiary, has really embraced JAX and started putting out lots of auxiliary packages around it. The Python array computing ecosystem is getting exciting once again, and my hope is also that it doesn't become fragmented like it did back in the pre-NumPy days. Definitely keep an eye out for the folks at Quantsite and in the broader PyData community. They're doing a lot of work to make sure that this fundamental piece of the PyData ecosystem stays coherent and interoperable. Okay, so now before we go on, I'd like to make sure we're all on the same page with respect to the prerequisite knowledge that we'll need for this tutorial. Just want to be clear, this isn't to exclude those who don't come in with the requisite knowledge but still signed up. I definitely still welcome your questions in the chat system. I'm just saying that if you possess this knowledge, it'll help you be a little less stuck when you encounter the exercises. Now, because JAX is written targeting the NumPy API in mind, familiarity with the NumPy API is probably a good thing to have. Things like what the universal functions are, that's pretty important. Also, knowing what a dot product is probably going to be really helpful because in our exercises, we use a lot of dot products inside there. Now, speaking about exercises, most of the exercises that you'll encounter in this tutorial are going to be array computing exercises. As such, having a mental model of what your array shapes look like will be pretty handy. And what I mean by that is if you're given a three-dimensional array, you can picture inside your head that it looks like a cube, might be elongated or something, and also that you're able to map out what the semantic meaning of each of the axes are to the problem that you have on hand. Okay, so next off, all of our exercises are written in Jupyter notebooks, and as such, you should be familiar with how to use Jupyter. Unlike Joel Gruss, who doesn't really like notebooks, I actually really do like them, and I can live with some of their limitations because the interactivity that I get is pretty amazing, and I think it's a great literate computing tool to author tutorials with exercises. So where can you go to access the tutorial material? Well, please head over to this URL over here. That's ericmjl.github.io/JAX dl-workshop, ericmjl.github.io/dl-workshop. Okay, finally, let's talk about the tutorial format. This video that you're watching is actually the first of a series of pre-recorded lectures that I've made. I do this because over 2 years of live training experience have taught me that I too have physical limitations, and my physical limitation is that I actually get a gag reflex when speaking for too long, and that the gag reflex very quickly drains my energy. So to keep the real life version of me energetic and refreshed for the live Q&A and the interactive portions of this tutorial, I've elected to invest the time up front to pre-record these lectures for you instead, thus leaving me a little bit more energetic for the interactive components. Apart from the pre-recorded lectures, there's also time budgeted for exercises and live Q&A in between videos. Definitely please take advantage of these time slots to ask questions. They keep the tutorial fun for everybody, including the real life flesh and blood version of myself watching this video alongside you all. As I mentioned earlier, there are also exercises in Jupyter Notebooks, and if you go to the appropriate pages, which I will point out for you later, you will find a launch binder button, one that looks something like this guy, on every page that you can click on. These are found on pages that were authored in Jupyter Notebooks, and therefore you can actually interact with them directly. So please take advantage of that. The exercises are a great way to get familiar with JAX. Okie dokes, if you're ready, then so am I. So let's get started, and I'll see you in the next video. Thank you. Okie dokes. So before we go on to the first video, I just wanted to check in with everybody and just ask a really quick question. Do you all have any questions so far about the logistics of how the tutorial is going to take place? And if you do, I'd love to invite you to speak up and ask those questions or put them inside the chat. And if not, let's try out the Zoom reactions. Let's see if you can do the thumbs up reaction. So if you're okay, give me the thumbs up reaction or do it in your camera. I'm seeing a whole bunch of thumbs ups. Okay, that sounds good. That's great. Awesomeness. Okay, so what I'm gonna do now is just gonna make sure everybody is able to see first I'm gonna make sure that everybody does have access to the official tutorial website. Okay, so ericmjl.github.io/dlworkshop. And like I mentioned inside the video, just make sure that you are able to, like throughout the website, any notebook that any page that was written as a notebook, you actually will be able to click on and open directly inside Binder. It's pretty awesome. It's pretty awesome of a system. Okay, so with that, I'm going to go on to the next pre-recorded lecture, which is going to be the one about us writing loops in NumPy, loopy code that otherwise would have been loopy and have magical access numbers that in a way that doesn't involve that loopy or magical access number code anymore. And you'll see in a moment through both the exercises and the examples how this can be pretty useful for writing really awesome, I would say clean functional code. So I'm going to share my video, share my window one more time, and let's get started with that lecture portion. Alrighty, let's start off by talking about loopless loops. In this section, we're going to be looking at this function that JAX provides called Vmap. Vmap is what we would call the first example of a functional transform. That is, it's a function that takes in another function and returns a modified version of that function. All right, so let's take a look at what the semantics of Vmap look like. So semantically, we start with a function called func. That's this one over here. What it does is it takes in an array X and does some computation, therefore returning a result. What Vmap does is return the equivalent of the original function, which looks something like this vmapped func over here. It takes in an array, this guy over here, that is basically like a stacked collection of subarrays that look like X, and applies the function across every single element inside array. That is, every single array that looks like X inside this stacked array itself. Effectively, it's applying the function across what we would call the leading axis or first axis in array. So to make things concrete, here's one example where we apply a function called square across the leading axis in an array. We start with an array that is of length 20. Therefore, its leading axis has 20 elements inside it. We then define the square function, which simply squares a float or integer. Then after that, we create the vmapped version of square. And finally, this vmapped version of square can be applied across that array A. Now, the astute amongst you will know that we didn't actually have to go through all this trouble, as the square operation will work element-wise, but stick with me, we're going to see another example where vmap's use will become pretty evident. Now, just to hammer away the takeaway point, vmap is actually a function, okay? And it takes in a function and returns another function. And that new function, by default, applies the original function across the leading axis of the array passed into it. Okay, so now what if we wanted to change the default behavior of mapping across the leading axis? Here's where we'll see another simplified example where you'll see where this vmap might come in handy. So here's another simplified example, this time with a reductive function called sum. So we have a sum vector which applies the summation operation over a single vector, okay? And what we can do is we can actually create a new function that applies the function sum vector across the leading axis, in this particular case over here, and we'll get the correct result expressed. So in this case, if we have an array A, which is of 4 rows and 5 columns, and we want to apply the sum vector across every single row, we'll get back a vector that is of length 4 because we're applying the function across each of the 4 rows inside this array A. Now, there is another thing that we can do, which is to change the in-axis argument of vmap. And what that will do is that will change the axis along which we apply the operation. Okay, so in this case, if we take sum vector and we apply it across all of the the zeroth, not the zeroth, the first axis, right? The index 1 axis, which is the columns, this function call over here will actually return a function that is now going to take in an array and apply some vector across every single column in the array that's passed in. And as such, we'll get something that is of length 5 once we pass in A. Here's another example that should help illustrate. And this one is with the softmax operation. When we have a matrix of numbers, right, and we want to get a row-wise softmax operation such that every row sums up to 1, we can actually set up the function to work the softmax function to operate as if it were working with only a single row of data, and then simply vmap them across every single row or every single column, depending on what you want. So one place where I've used this before is actually in calculating or estimating the transition matrix of a Markov model. We need the softmax operation to transform our estimates into a row-wise probability vector, which is the definition of what a transition matrix needs to have. Okay, now let's say you have a function that takes in two arguments, both of them being arrays. In this case, Vmap will actually automatically map the function over the leading axis of both arrays when passed in. Okay, we've hopefully gone through enough examples for you to get a feel for how Vmap works. All of the examples that we went through are actually inside the appropriate notebook as well. So we're now going to work on the exercises. The notebook that we're going to work on is titled Loopless Loops under the JAX idioms section, and we'll budget approximately 15 minutes of time for the exercises. I will be available on the chat system to answer questions at the same time, and then we'll gather back for the next section. Okay, I'm going to very quickly point out which exact notebook we're going to go through. Let me just share my screen, this window over here. So we're actually going to go to the notebook called Loopless Loops, and it's over here. And if you go to the top of the page, you'll see that Launch Binder button. If you click on that button, it'll open a new tab, and that will bring you over to a binder session. Give it a moment or two. I made sure this morning that I clicked on that button to make sure that there's a pre-cached container, so nobody has to wait for the container to be built. And you'll be brought directly into the exact Jupyter notebook that is of interest. And for those of you who prefer using the lab interface rather than the notebook interface, if I remember correctly, you can actually do this thing where you go /lab on your personalized URL on the screen. And that will bring you to the Jupyter Lab interface. Yes, that's right. There we go. That'll bring you to the Jupyter Lab interface. And the notebooks are on the left-hand side. We're inside the JAX idioms folder. And that particular notebook is the one that we will be using today. A few reminders for yourself. Binder does have a timeout. So if you want to keep your binder session live while we're going through the videos, just make sure you execute something, execute a cell. You can even say x equals 2 in a dummy cell, and that will keep your binder session alive. I think the timeout is about 15 minutes, but just to be on the safe side, every 5 minutes or 10 minutes, execute something to keep it live. Okay, so before I leave you all to do the exercises, I just wanted to stop and ask, do we have any questions on Vmap? Vmap is the first function that first piece of JAX that I think makes JAX pretty magical. And I just want to ask if you all have any questions surrounding this function before we go on to the exercises. If you're okay, give me a thumbs up. And if you'd like to ask a question, there's the raise hand thing as well. I'm seeing a whole bunch of thumbs showing up, which I think means we should go to the exercises. So let's budget 20 minutes. And when you're done, just so that I can keep a running tally of who's finished the exercises, please drop like a I'm done +1, yes, or whatever inside the chat once you're done with this particular notebook. Okay? And I will be here, I will be up here. We have a question from Tanya. I'm going to ask you to unmute so you can ask, yeah, I'm going to ask you to unmute so that you can ask the question.
Yeah, sorry. I raised my hand, then you're like, oh, nobody wants to ask. Like,
I'm sorry. My apologies. I'm glad you actually asked. I'm glad you like pipped up inside the chat because I had the chat open up on. Yes.
Yeah, I mean, the main thing I'm just kind of curious about, are there other kinds of tools out there that you're aware of that do similar things to JAX? I mean, I never heard of JAX at all before this. The closest things that I've seen that I've applied that kind of do what you're doing, I mean, first off, there's the Python decorators, but with those, I can see JAX is better in that you can configure the axis, which is nice. And then I've used Dask for applying functions, to things row by row.
Yep.
I don't know, is JAX like, is it more like it's really fine tuned to NumPy arrays, or it's like an efficiency kind of thing? I'm just wondering what else is out there and what JAX's advantages might be.
Definitely. So I'll unpack the question a little bit.
Mm-hmm.
I think one of the questions you're asking is
Mm-hmm.
are there tools that do things that are similar to JAX?
Mm-hmm.
And with respect to, and when we say like what are similar things, there are a few categories. The first one is this functional transformation of this transformation of a function into another function to do some other things. I think for that, I personally have not seen another system that does similar things as JAX.
Mm-hmm.
So for that piece, I don't think there is. There is one category of things that JAX does that is, I think, replicated by Numba, that is just-in-time compilation of
Mm-hmm.
your array-oriented code. Numba is trying to become more of a slightly more general purpose just-in-time compiler,
Mm-hmm.
whereas JAX really is just focused on arrays.
Mm-hmm.
So that's another, I think that's another comparison that we can make. The
Mm-hmm.
third category of things that I think are uh, unmatched in the Python ecosystem, at least, is automatic differentiation. Automatic differentiation is one thing that we will go through later in the tutorial.
Mm-hmm.
Autodiff is available in other systems. Actually, I take that back. The old Theano, PyTorch, etc., they all have an autodiff system of some kind backing
Mm-hmm.
them. But I think what's unique about JAX's autodiff system is it's just the way that it works, the syntax, all of that just feels a lot more like writing math, and we'll see an
Mm-hmm.
example of that later on.
Okay.
Yeah. So I'm gonna pause here, and I'm just gonna while everyone else goes on with the exercises, I'm just gonna ask you if I missed something in your question, because I know that it was a bit of a slightly bigger
Yeah,
question.
I was kind of yeah, I was sort of asking several questions while I was kind of thinking out loud.
Yeah.
But I think you addressed the different points altogether. So yeah, I'm good.
Okay, dokes. Cool.
And I think it'll probably become clearer too also when we get to those other examples like you mentioned.
Definitely, definitely.
Yeah.
And I think one thing, like I mentioned in the video, pay attention to the Python array ecosystem, because it's there's a lot of activity that's happening in terms of, we've got core arrays now. People want to extend core arrays in a bunch of different ways. And how do we encourage this innovation without stifling it too early by standardizing on stuff, is like one major problem that the people at Quantsite are doing. Ralph Gommers and co at Quantsite Labs, they're really worried, concerned, and thinking hard about how to bring the community together around this problem. So it's definitely something to keep an eye out for. I think one of the ways I approach JAX is, yes, I can use it for really productive things, but I also recognize that it's one of multiple experiments in extending the array ecosystem library, array ecosystem in Python.
Mhm.
Okay, thank you, Tanya. Appreciate the
Mhm.
question. Okay, so I'm gonna just let everybody go on with the exercises and I'll mute myself so I don't disturb anybody over here. And we'll probably reconvene at 11:50 for a little discussion. Then I'll let everybody go for a short break. Okay, it's 11:50. I just wanted to get a feel for where people are. If you're done with the exercises, can you give me a thumbs up? No. Okay. Yes, I will admit I did set some pretty challenging exercises. So what I think I will do for the 10 minutes leading up to the hours, I'll actually explain the solutions with an emphasis on how we use the Vmap function. Okay. And I will preface this. I forgot to mention this at the beginning, and usually I do. I don't know why I forgot it this time around. If you ever feel stuck, there are actually solutions. And what I'm going to do, this is just perfect. I'm going to share my screen one more time. I'm going to show you where all the solutions can be found. So if you notice there, if you go to the root of the tutorial repository, there's actually a source folder. And in the source folder, there's the DL workshop. That's where this like DL workshop import is coming from. It's coming from a custom library that's packaged with the entire tutorial. And then in the DL workshop, for every section that has exercises, I actually do put the exact, there is a corresponding .py file that contains all of the functions. And so all of the exercise answers that you might be interested in for the coming tutorial, for this tutorial, are actually inside there. Okay, so what I think I'll do is, let me just drag this over to my bigger screen. And can I just confirm? No, okay, my screen share got paused. Now my screen share should be back. So I'm gonna very quickly walk you all through how we use Vmap in how to think of Vmap. Okay, so actually this is a very good time to test drive the whiteboard. So I'm going to do this. I really can't resist this one. It's a pretty cool piece of tech. So I've pasted in the chat a link to a whiteboard that I think everyone should be able to access. And if any of you access it and want to start drawing directly on there, I won't mind. It's something that is intended for us to all pretend we're in like a real room and interacting with one another. So I wanted to bring your attention to how we think about Vmaps, all right? Essentially, pictorially, Vmap looks something like this guy at the top over here. If you start with a function, that's this one over here, okay? And it accepts an array and returns an array, just like it does over here, okay? Then what Vmap does is it essentially, the Vmapped version of this function will be able to take in an array that has one extra axis and return the array, return the corresponding stacked up results. So if you have another array like this guy over here, another function like this one over here that takes in an array and returns a scalar, that's this one over here, then the Vmapped version will return a stack of scalars, right? And that stack of scalars basically is just a vector, all right? So I'm just gonna undo all of these, clean up the whiteboard a little bit. Okay. So if we go back to the exercise, let me see here. If you want to do a Vmapped message passing, that is effectively taking a dot product that accepts in two arrays and it returns back a single array. So I'm going to draw this out on the whiteboard for you all. So let me just see. Erase the top one. Okay. So let's say I have a func. Actually, we'll follow the exercise. So it's called message passing, and it accepts a square array called A and a perhaps rectangular array called F, and it returns a rectangular array called f prime, which is like a message passing version of a. What message passing exactly is, I'm not going to explain it over here. I explained that in the network analysis made simple tutorial, which is also freely available online for all to take a look at. So with what the exercise is asking for then, so let me just do one other thing. I'm going to annotate the shape of these axes. This is n by n, okay? And this is n by f. So this is n, and that's by f, and you return an n by f array at the end, okay? Let's make a little bit more room down below. What we're going for then is we want to Vmap MP over a stack of A's. So this is now n by k, and k feature matrices as well. So we'll do, oh my drawing is horrible. Let's try that again. K by n by f to get back another array that is k by n by f. Okay, so I'm going to pause here and just ask everybody really quickly, are we stuck somewhere? Let's see. Yeah, when screen sharing happens, all of the controls go away. Let's see. Do we have questions so far? So you'll notice over here that now this k by n thing and this, oopsies, come on. And this k by n by f thing, the leading axis is this, oopsies, oh man, I'm on two systems. The leading axis is k. And so what Vmap allows us to do is to map the message passing function across every single element along the leading axis, the 0th axis, okay? And so that's the core of what Vmap does. It allows us to, like I mentioned, take a function and transform it such that it now accepts basically stacked versions of the original data that it would accept, such that the function is applied across every single element in that leading axis, okay? Questions so far about this one? Okay. If not, I'm going to very quickly explain that second, I'm going to explain that second one as well. Okay, so let me see. Oh, loopless loops. Okay, so that second exercise, you'll notice that it basically follows that exact same pattern, right? So I have a data set that has one extra axis, but my elementary computation takes in something that is of n rows by n columns. So what I do first is I define a function that operates on the elementary data structure, and that forms my elementary operation. And then what Vmap allows me to do is to Vmap that function that performs the elementary computation across every element in the leading axis. Now, the one that gets really complicated is actually this Loopless loops exercise 3, which is the one where we're trying to do a double for loop using Vmapping only. And this is the one where I said it does require something called like function partialing in order for this to work. I probably should have mentioned this at the beginning. My apologies. You probably do want to know a little bit of what functools.partial does because it helps us fix certain arguments. We'll actually, we'll see another example of it later in the tutorial. So here's how this one works. What we're trying to do, let me go back to the whiteboard and come back up here. And let me just see, I'm gonna make sure I'm syncing up my view on my tablet. So let's erase all of this. Just very quickly, I want to take a thing that is of this particular shape, n by f, and I would like to create a version of it that is n by 2f. And so that version of it that is n by 2f is actually along each of, along each, like if you view the array from the front, that's this n by n face, you'll and you go backwards into the array, it has the f vector, that's one of these guys over here, stacked up with any one of its corresponding other partners. So in this one, it would be the 0th one and the 0th one stacked up together. In that next slot over here, right? That would be, oh, my drawing. That one would be the 0th row with the first row, et cetera, et cetera. And so in the solution, if you go back and ponder it for a moment, this one, what we start with is we start with this concatenate operation, and it takes in 2 arguments, the n1 and n2. And what we do first is then we define another function that operates assuming we have a particular node under consideration, but we have all of the other n by f features stacked up and available over there. We partial that one and fix concat to that particular one, and then we vmap that concat function across every other member inside node feats, and then we vmap that one yet again. We vmap concat in an outer loop to return the result of interest. Now, what I would encourage you to do is maybe offline or afterwards, I'll hang out inside the lounge area as well for your benefit. We can talk about this like partialing pattern and the likes afterwards as well, but I definitely encourage you to like deconstruct this answer into its component functions and sort of see what happens when you do every step inside there. Okay, so don't worry if you didn't get these exercises the first time round.
Quick question, if you don't mind.
Yes.
What does partial do? It does the interaction of the 2 different arrays, and is it kind of like a Vmap where it's like more like a function kind of?
Yeah. I'm sorry. Thanks. Scott, is that you?
Oh, I'm sorry. This is Jonathan.
Jonathan.
Yeah,
okay.
just a little detail on what the partial's doing. If you
yeah, totally. Thanks for catching me on that one. Okay, so I'm going to illustrate live what this does. Did I lose my binder session? Oh, please don't. So this is why you should execute code. Thanks, Jonathan. I'm going to explain very quickly what partial does, all right? So from functools, import partial. Let's say I have a function that does multiplication. Okay, and I return x times y. What partial allows me to do is it allows me to set one of these arguments to a fixed value such that, and it will return another function with that particular property. So let's do this, for example. Mul x is partial of multiply where y is equal to 4. Sorry, multiplied by 4, right? And so now I can pass in any value of x, and it will take that value of x and multiply it by 4. Will give me 12. So that's the simple version of it. You can actually have really complicated operations that happen inside, but all that partial does is it operates on the arguments, and it says fix the value of this one, of this particular argument to be a particular value, right? And so, Jonathan, did I answer your question over there?
Yes, thank you. I thought that that's what it was doing, but like, thank you for explaining with a concrete detail.
Not a problem. Actually, this was important, and I probably should have explained this before throwing everyone into the deep end. So, like I mentioned, don't feel bad if you didn't get it the first time around. That double for loop thing, that exercise actually took me a whole afternoon of thinking. So I clearly didn't expect you all to do it, but that's why I wrote the answers so that you can go back and study it and sort of like deconstruct it in your head. I think it's as I wrote inside the chat, the answers are always transparently available in case you ever feel stuck. And my intent here is that I study things by learning. I study solutions to learn things. And I think we shouldn't feel bad about doing so. And yeah, so that's my hope for you all as well. Okay, so we're a little over, and I think it's a good time for us to go for a little bio break. So we'll come back at 12. Do you all prefer 12:10 or 12:15? Let's if you prefer 12:10, give me a thumbs up on the Zoom system, and if you like 12:15, give me a wave. Okay, I see one vote for 12:10. 12:15, 12:15. They're popping up. 12:15, 12:10. Okay, let's do. I think I get a rough sense. I have a Bayesian feel for this, so let's do a 12:15 return for our break, and so we'll see you all back with the next video. And yes, I forgot to mention it's 12:15 Eastern time because we're all over the world right now.
Just want to give folks a heads up. We've got about 2 minutes left in the break.
Okie dokes, it's 12:15. That means I think we're probably ready to go into the next part of the tutorial. And so for this part of the tutorial, we're going to look at another loop replacement that JAX provides. And that loop replacement is called Lax.scan. And I think it's a pretty powerful function to have on hand. So I'm going to share my screen as usual, and we'll do a quick video play just to, let me just make sure that my audio is sharing. Yes, share the sound. That's good. Okay. So yeah, let's take a look at the video, and then I'll launch everybody onto the exercises. Welcome back. We're now going to go to the next section called loopy carry. In the previous section, we looked at Vmap, and Vmap is basically a function that works well with other functions that operate on axes independently. If you need an anchoring example to help you remember what's going on, think of Vmap as something that applies a function over every single row in a table independently. But that might not be the only kind of array operation that we might need. What if we need something that calculates, what if we need something that does a calculation where the result of the current iteration has to influence the next iteration? Or put the other way, the current iteration requires the result of the previous iteration to do its calculation. Well, to do that, we need to go a little bit deeper into JAX and use this function called scan, which is located in the Lax submodule. Okay, but first, we probably should dispel some questions around what exactly Lax is. To start, we have to know that JAX implements the NumPy API on top of the XLA library. It doesn't simply wrap NumPy, it's actually a complete re-implementation of the NumPy API with a different backing array library. And so what exactly is XLA? Well, XLA is the Accelerated Linear Algebra library provided by Google. It's most often associated with the TensorFlow project, but at the same time, JAX relies basically exclusively on it. So Lax then is a Python wrapper around the primitive math operations that are implemented in XLA, plus a little bit more for loop constructs. And in particular, Lax.scan implements looping with carryover between loops. Here's an example of the semantics of Lax.scan as documented in the JAX docs. So Lax.scan takes in a function, right, function f, that has a signature carry and x. What carry is it's the thing that's carried over from the previous loop iteration to be operated on in the current iteration, while x is the current loop element, say an element in an array. And what this function does is it returns a tuple of the new value to be carried over, which is this thing carry over here, as well as the result to be accumulated, which is y over there. And so at the end, the final carryover value and the stacked y are returned. So here's one example of Lax.scan in action. Here we are trying to calculate the cumulative sum over an array. We set up the function to accept res, which is the carryover, and L, which is the current element in the array. Now inside the function, we calculate res by updating its value. And because we are interested in carrying over res and accumulating it to get the cumulative sum across the array, we return res and res as a two-tuple. And if you try this example inside the notebook, you'll see that the result matches np.cumsum. So where does this loopy carry or Lax.scan get used? As I mentioned in the beginning, I was actually learning a few model classes like recurrent neural nets and hidden Markov models with my colleagues and interns. And it turns out that Lax.scan is really important for doing this autoregressive sort of time series thing where, like we mentioned, the current result depends on the output of the previous result. I've also used it to simulate Gaussian random walks, and you'll get a chance to do the same in the exercises below. And so speaking of which, we're going to go to the exercises now. Just as with the last set of exercises, there's time budgeted for it. I think we'll do 15 minutes. Same rules as before, ask questions in the chat as they show up and I'll respond over there. So please go ahead, have fun with the exercises, and we'll see you back in the next video. Okie dokes, everyone. So we're going to go to the exercises, as I mentioned, and seeing the difficulty level, especially with, I think the core difficulty here is wrapping our heads around a functional style of programming and thinking about what happens on a function level rather than a more procedural level that most of us might be accustomed to. What I'm going to ask is you do your best attempt at trying whatever exercises you can. Don't feel pressured at all to complete all of them. That's the last thing that I want. I want everybody to have fun with array puzzles here rather than feel pressured to like, I must finish this exercise, everything here before the time limit comes. I just want to remind you all, like the content is all available online for free and you can always come back and explore it on your own time too. And what I will do is I will at the end do what we did for Vmap as well. I'll sort of try to use illustrations to help reinforce the core idea behind this time Lax.scan, and then hopefully that will give you a good base on your own exploration afterwards as well. Okay, so we'll budget again 20 minutes for this, plus then a 10-minute time, 10 minutes for a bit of a 10 minutes for a bit of a discussion and questions. So we'll go until 12:40 p.m. or 40 minutes after the hour on my side, and we'll gather back for another discussion. Okay. And I must say, Thomas, I really appreciate all the video feedback that you're giving. It helps me a lot. Alrighty, it's 12:40, 40 minutes after the hour. So what I'm going to do is I'm going to do two things over here. I'm going to reiterate what the core idiom for Lax.scan is with using a, well, at least my own core, what do we call it? Anchoring example, okay? And then I'm going to give you a few pointers on what the exercises actually emphasize with respect to composable program transforms, because we're starting to see this thing where we can compose more than just Vmap or Lax.scan alone in the exercises. So I'm going to start first by explaining a little bit about what my anchoring example for Lax.scan is. Okay. So I'm going to go over to my whiteboard. Okay. That's this window. Let's see. Come on. Resume share. So my anchoring example is a financial one. It's because my wife is in finance. And the core idea here is basically best expressed using compound interest. So if you remember Lax.scan as a function, it accepts a function f for which we need to have a carryover and x. That's the core thing that Lax.scan has to accept. So if you think about compound interest, Lax.scan accepts this function, but it also accepts an initial state, because every time you do something with loopy, with carryover, you're always presuming that you have an initial state that the program is in. So in this case, let's talk about our initial state being our wealth at time 0, or the wealth that we're trying to compound over time. And so to do compound interest with Lax.scan, you have to remember what we're carrying over. That's this guy over here, okay, as well as what we're accumulating over time. That's this one over there. So inside the function, the body of the function is encapsulated by what's happening in this column, the W column, where we're doing the actual calculation. So the initial state is this one. At time step, oh, sorry, the other thing that Lax.scan also accepts is this like array of things, right? So this final array of things that we're interested in is, in our case for compound interest, just a time step. We're not really going to do computations over this time step, but it's like there for convenience. So you can instantiate it as something like np.1s of length however long you want to go, because we're not going to use this, or you can do it as np.a range for however many time steps you want. Okay, so the important thing to remember is you always must return a carry, and you always must return something that you're trying to accumulate. So in this case, since our initial state is this guy, what we want to accumulate over time, starting with the initial thing gets passed into the carry function, the carry argument of the first function call, and then we use that to calculate the result that we're interested in. Now, we're trying to carry over this into the next time step. So the carry return will be this guy. And because we're trying to find out how much we'll have over time and we want our wealth to be indexed correctly, we don't return W1, we return W0. Now, if you wanted to ignore W0, you totally can. But in this case, we're trying to make sure the initial wealth is captured. So we'll return W0 as part of the thing that we accumulate. And what happens at the end is we sort of we stack up all of these accumulates together, and we return at the same time the final value of the carryover. Okay, so I'm going to stop here. Can I undo that? No, I can't undo that. Can I? Okay, so I'm going to stop here for a moment and ask, are there any questions with respect to Lax.scan, right? The semantics of Lax.scan. So I know that there's an example. There's the pseudocode, or rather Python equivalent of what Lax.scan is doing. If you need to make it more concrete, I would think about compound interest. And the most important thing for you to remember is what exactly is the carryover and what exactly are you trying to accumulate, okay? If you find yourself writing loops that look something like this one over here, right? So if you find yourself writing at first a naive loop, that's totally fine, right? You write the loop to prototype your logic. If you find yourself doing things where like, oh, I'm assigning a loop thing to be a new value and the likes, right? And then I'm using this in the next loop iteration, that's a function, that's probably something that you can stick inside, like the loop body is something you can probably stick inside a function, which you then Lax.scan, all right? So, okay, so we have the anchoring example. It's one of the exercises. And if you attempt it later on your own time, that's something that hopefully will help you remember what's going on. What I wanted to highlight in the exercise below is how we can, if we can encapsulate the compound interest calculation over time inside a single function, then actually we can Vmap that function over multiple starting points and, you know, have this bigger program that that will, how do I put it? It's like, it's very, very, it's like you can Vmap over a bunch of starting points and get back an array result. And I think I heard someone pip up a question. So I'd like to invite them to come up and say what, ask that question. Or was there not? Okay, maybe we can give that a, whoever picked up, please go ahead, put your question or like raise your hand, and I'm happy to address that question. So this is an example of composing together Lax.scan and Vmap together to create this bigger program that lets you run lots of simulations in parallel. All right. Well, okay. Parallel is an overloaded word. With a single function call, you can run multiple simulations. And this is an example of what we would call staging out your computation before actually executing it. So it's sort of a departure from a procedural style programming which Python's really good for, right? You can procedurally, you know, write your code and sort of set values in exactly the way you want. You can write double for loops as well. But if you're able to, in your head, think about the inner loop bodies as functions and every loop body as like a function that you can sort of scan or map across an array axis, then actually you're setting yourself up for a lot of success in making really high performing numerical array computations happen with nothing more than just Python code plus a little bit of JAX magic sprinkled in. Okay, so I got this comment from Thomas, which is didn't accumulate the init value, so it was off by 1. But yes, yeah, so that's definitely something to keep in mind. The test is a little strict, but I think if you did it your way, Thomas, that's, I mean, as long as it fulfills the requirements of your program, that's fine. You don't have to worry about the off by 1 thing. As long as you get the sort of, I carry over and I accumulate something, that's the main piece to keep in mind. And this second example, stick breaking process, is something, it is actually literally lifted. It's an exercise that's lifted from something that I had to do at work, where we were trying to study completely non-parametric, Bayesian non-parametric models for clustering. And I wanted to make sure I really understood the math behind the Dirichlet process as implemented in a stick breaking process. So this is an example that's taken from me trying to figure out what in the world is going on with the stick breaking process. And so if you get this one, there's actually one notebook under Gaussian clustering on the website that is that will reference sort of the stick breaking process as well. And you can actually use that notebook to study some things about. Yeah, you can use that. How do I put it? You can use that notebook to see some really cool things that you can do with gradient-based and fully probabilistic gradient-based optimization and fully probabilistic models written entirely in JAX, compiled in these crazy ways. It's really, really cool. And I would recommend that as like post-tutorial exploration if you have the time. Cool. So I'm going to pause for a moment for questions. Do we have any questions with respect to this section? Stop my screen share for a moment. Any questions so far? Anything that's like bugging you, that's a little bit, that's worrying you? If you have no questions, give me a thumbs up, either by the Zoom system or in the camera. If you have a question, wave, and I'm happy to address them. Let's just seeing lots of thumbs up. People seem to be good with this tutorial. You all are like pros. Okay. If we've got no questions so far, I think it's a good opportunity for maybe another break. We'll do a short one, so we'll go for 5 minutes. So 12:56, I'll come back, and then we're gonna try to see what we can finish up. And if we can't finish all of the pre-recorded lectures, I will make sure that in my message, post-tutorial message, that the Dropbox link is sent to everybody so you can actually explore the videos on your own time. Okay. So let's take a quick break. 12:56. Let's come back. Okay, let's come back, finish with the break. We're going to go back and go on, and we're going to do the notebook on deterministic randomness. So that's the next thing that we'll explore over here. So I'm going to very quickly do my screen share and play the video for you all. And let's get going. Welcome back. In this section, we're going to see how JAX's way of handling random number generation makes it so much easier for us to debug issues when we're writing stochastic programs. If you've ever tried drawing random numbers in NumPy, you'll probably end up writing something that looks like this. Say you started with a random seed for your program, and then in the next 2 Jupyter cells below it, you sequentially drew 2 random numbers. Now, if you ran cell number 2 once more accidentally, you'd overwrite the value of A with a different value. That's actually problematic, because if your original value of A gave you an error, while the new value of A didn't, you might actually end up spending a ton of time trying to debug what exactly happened before finally giving in and restarting the kernel. I know that because I encountered that exact issue when I was trying to debug a program that involved MCMC sampling before, and it was intensely frustrating to handle a bug that popped up only once every 13 runs. The problem here is implicitness in the way that we're generating our random numbers. And as you know, for those of you who are familiar with the Zen of Python, explicit is actually better than implicit. So rather than explicitly setting a seed for each random number draw, with vanilla NumPy random number generation, we actually have a stateful global seed that implicitly controls draws from the start of our session. But JAX, by contrast, enforces full explicitness and therefore determinism in our random number draws by requiring a pseudo-random number generator key, analogous to the random seed that we set, to be explicitly passed into each of the random number generating functions. As you can see in this code cell, the PRNG key basically determines the draw, right? Passing in the exact same key into random.normal makes sure that we get the exact same draw that comes out from it. And as you can see in this next code example, we explicitly have to split the key if we want to get a new number from that first draw. So that means if we want to generate arrays of random numbers, there are actually 2 different ways to handle this. The first way leverages what we've learned before, which is to create 20 keys by taking the original master key and splitting it 20 ways, and then vmapping our random number generator function across each key. Of course, the simpler way to do this is to specify the shape that we're interested, shape of the random number draws that we're interested in obtaining explicitly. So I definitely want you to notice how the draws were different, because the keys that were passed into that first function were the descendants of the master key, while in the second case we passed in the master key itself. Here's another example using the Gaussian random walk. The Gaussian random walk is actually defined as a stochastic process where at each time step, a random number is drawn from a Gaussian and added to the previous value drawn, starting of course with a draw from a Gaussian itself. And that's basically the Gaussian random walk that I was talking about in the previous sections. The code looks something like this, and basically we need to, if we're interested in having 200 time steps, 200 different random number draws, then we first split our key 200 times, 200 ways, and iterate over it such that we add a normal distribution to draw to the value of mu that gets updated in every single loop. Now, if you look at the Gaussian random walk, that kind of loopy carryover looks kind of familiar, right? We just learned about that. So it appears, this is basically what the Gaussian random walk will look like. So yeah, it looks pretty familiar, and that's because that was a Lax.scan, right? So we can write this in JAX without writing a for loop. This is basically a stochastic program combined with looping. And so the way that we do this is we actually instantiate an array of PRNG keys, and then we scan a Gaussian random walk function over the array of keys and collect the observations together. Here's an example of that. So if we take a new draw, we need the previous value, and we need a key such that we can generate another random draw. So the new draw over here is the value of the previous draw, previous value plus a draw from a Gaussian, and we return a new draw while accumulating the previous draw. And if we go ahead and plot that, it too is a Gaussian random walk. So now there's going to be an exercise that you're going to attempt in a moment later in the tutorial. And I wanted to just go over the logic really quickly so that nobody feels too stuck when they're handling it. What if you wanted to do multiple draws of a random Gaussian random walk? This is one draw, meaning we produce one curve. What if you wanted multiple curves? Well, one of the things that we can do is we can actually leverage even Vmap that we had. And so what we'll want to do is we'll actually want to encapsulate one draw inside a function and then Vmap that function across multiple starter PRNG keys. Notice how over here we are using a functools partial, right? Which partially evaluates a function, effectively fixing the value of num steps in this particular case to a fixed value of 1000. This makes sure that when we do the Vmap, we're Vmapping only across the key array 0th axis, and we're not worrying about the integer num steps argument, all right? And in this particular case, this GRW is a very, very simple example of what we might call staging out the computation. So I like to think of this idea as being anchored on this thing where we're identifying the repeatable units of computation and then finding creative ways to Vmap and scan them. And as you read through the examples that we've placed in the notebooks, you should be able to see that we've basically composed Vmap, scan, random number generation all together into this single but moderately complex stochastic program. And the most important piece here is the results from this single moderately complex stochastic program are actually deterministically reproducible given a single master key. Okay, so let's go do some of the exercises now. The notebook we'll be using is called Deterministic Randomness. Same rules as before. Ask questions in the chat as they show up and I'll respond over there, and we'll gather back in a moment and I'll see you in the next video. Okie dokes. So I'm going to very quickly show you all which notebook we're going to be working with. It's the Deterministic Randomness notebook. Let me just share my screen real quick. There we go. So we're going to be using the Deterministic Randomness notebook. If you're in the website, you can go to the navigation on the left and click the Launch Binder button. And I think this will be the final section that we'll be able to cover today. There is one more, which is on the automatic differentiation capabilities of JAX. We won't be able to cover it by the end of 1:30 because of the time I'd like to budget to make sure you have enough time for exercises. So what I'll do at the end is I'll just give you a quick overview of what's inside that notebook, and then we'll wrap up, all right? And we'll wrap up with like all of the things that I'm hoping you should have learned from today's tutorial, all right? So let's go until 1:25. 25 minutes after the clock for the deterministic randomness notebook. And we'll gather back after that, all right? Tanya, you've got a question. I'd like to invite you to go ahead and ask it while others are doing the exercise.
Yeah, so my question actually doesn't have to do with the exercise. It's just that I was kind of thinking about what this library is capable of, and we're kind of wrapping up. So one thing that we didn't really get to talk about in the workshop was like sort of like the performance of the library. And looking online, there's certain decorators like just-in-time compilation decorators that you can apply to functions. And what I was wondering, I know that with these tutorials, you come in and you're like, hey, look, this library is amazing, and show all the great things about it. I'm wondering if you ever ran into any potential like maybe downsides to it with the library, specifically with configuring it for these kinds of optimizations. And I ask because in the past, I've never actually gone too deep in it, but like you brought up Numba before. I tried applying Numba before, and the thing is online, they show these magic examples where you apply it on an array, and it's like, oh, okay, look how fast this is, and it's nice. But when you apply it to more complicated code, and in particular, like object-oriented code within classes, I just found that to be a big configuration headache. And so I was wondering if JAX, if it's a similar headache applying it to functions within classes. That's one thing I'm wondering if you've ever come across that.
Yeah, totally. So JAX, as I think in the chat there was this point raised that JAX does encourage a slightly more functional style of programming. And so whenever I write my JAX programs, I try as hard as I can to stick to functional programming idioms. So that does mean things like knowing how to partial out functions and keeping track of functions that are returned from, different partials and the likes. I think that's one of the downsides more likely of functional style programming than class-based programming. With class-based programming, you can always rely on, I'll just keep that as state and then I'll pass it around inside my class. But with functional style programming, if you want to maintain state, you have to explicitly partial it out, which then makes it really forces me, the program writer, to go, okay, what exactly do I need in terms of my program? And it forces me to stage out think a little bit more thoroughly about what exactly the computation is that I'm trying to do. So I would consider that, you could call it a downside. It's something that people need to get used to when they're first encountering JAX, right? There's, with respect to things like compilation and the likes, I think this is going to be a problem with any library that tries to do just-in-time compilation of Python code. You have to worry so much about the dynamic typing system that if you don't restrict yourself a little bit or try to impose some assumptions, it's going to be really hard, right? So with JAX code, thankfully, they say the JAX devs have said, we're just going to target NumPy and NumPy arrays, and we're not going to do any of the fancier array types like sparse arrays or whatever. It's just going to be NumPy arrays, and we're going to target the NumPy API. And as long as you write array code, you're cool, right? And I think that simplifies a lot of what we need to worry about as people who write numeric array code. As long as I can, in my head, picture what is it exactly of the cube of data that I'm going to deal with, plus maybe what kind of new cubes of data are produced from functions that take in older cubes of data, then I think we'll keep ourselves in a very, very safe position. And when it came to then layering on other APIs, like let's say for example, we have a recurrent neural net that we used for protein engineering, sped it up over 100-fold over like TensorFlow 1.x. It's 1.x, right? So what do you expect? after speeding it up, we realized the API could use a little bit of work. So what we did was we had a few options. I actually did a test drive where we were like, let's try to embed this function inside a scikit-learn-like class-based API. And it works fine, right? Just as long as the underlying computations are all just pure functions. Nobody, like, you can wrap around that pure functional thing, class-based API, and you're totally okay. What we eventually ended up doing, though, was trying to support protein engineering workflows. We actually, instead of trying to be generic, we wrote explicit, like, evotune function, which is the equivalent of fit for a number of steps, right? Fit a model on some data for a number of steps, but we instead just named it evolutionary tuning because that's the concept in protein engineering that we're trying to support. And we stuck with just functions all the way through. And I think in making that design choice, it helped. That said, though, there are other projects where it's like slightly more generic. The model was slightly more generic and the application space was slightly more generic. We were able to safely put that model function inside a scikit, wrapped with a scikit-learn API around it, and that was totally fine. And so then the main point being, if you think carefully about your computation and write everything as pure functions, no side effects, no states involved, you can, at the final highest level, wrap whatever API you want around it, and you're totally okay.
Okay, cool. Thank you.
Thanks for the questions, Tanya. I appreciate them.
Yeah, thank you.
Cool stuff. So we're going to wrap up now. I just wanted to very quickly tell you what that final notebook and final lecture that we're not going to be able to go through is all about. It's about GRAD, the automatic differentiation system that JAX provides. It is rad. I really like it. I'm one who who hates algebra, like it or not. I don't really like algebra, and doing derivatives with like complex functions is, with complicated functions is kind of a chore for me. So if I can write my entire function inside NumPy, I can actually just call grad to get the derivative functions just like that. And it's all predicated on the chain rule and the likes. Won't elaborate too much about it over here. But if you go through that notebook, and I'll send the link for the pre-recorded lecture as well to everyone, you're gonna, I think you'll fall in love with grad. It'll save you a lot of time doing calculus. Cool. And then you can use grad, of course, to do things like gradient-based optimization. And there's an example inside there. And finally, when you're done with the entire thing, if you really want to see an example of how you combine Lax.scan, Vmap, random generator keys, and grad all together with just-in-time compilation as well inside a single, slightly more complex program, head over to the section called the Stacks module and look at the linear models with Stacks notebook. That one is like one that took me a little bit of time to write, but once I wrote that, I fully understood. Oh yeah, I can just compose JAX's Vmap with grad with JIT together and write this semi-complex program and get so much mileage out of the code base that I wrote. All right, so that's something I definitely encourage you all to go and check out once we're done with the tutorial. Mike has, thank you very much. You've dropped the link for the lecture video segments, and in this email, which I'm going to send right now, I also included the link, so you'll have it inside your inboxes pretty quickly. So once again, I want to thank everyone for coming. We're at the finish of the tutorial. Hopefully you learned something as much as much of something that I learned from writing this tutorial myself. I'm going to hang out inside the lounge area on the platform. There is a lounge area for us. It's I think at the top, and it's called Magical NumPy with JAX. And I'll just hang out there for about half an hour. My stomach's on the verge of rumbling, so I probably will drop off at 2. my time, 2 p.m. my time, to have a little bit of food. So once again, thank you everyone for coming. Hope to see you all around in person sometime soon, or if not, virtually throughout the conference as well. All right, so see you everybody. Thanks a lot. Back to you, Mike.
Great. I'm going to stop recording.